tiny particles, the energy waves, you'd kind of assume they're all, playing by similar rules.
But some of them, well, they're operating on a completely different level, almost like ghosts passing right through us.
That's a perfect way to put it. And that's what we're diving into today, right? This really fascinating world of fundamental particles and radiation.
Exactly. Our mission, if you will, is to sort of tease apart the differences between neutrinos and photons, plus other radiation you hear about, alpha, beta, gamma.
Yeah. We've looked at some really interesting sources that highlight these differences. And, why should you care? Because getting a handle on these tiny things, it actually unlocks some huge secrets.
Huge secrets. We're talking about how stars work, the structure of the cosmos. It touches on particle physics, astrophysics, nuclear science. It all connects.
It's surprisingly relevant.
And we want to make it clear, fascinating, without just drowning you in technical terms. The goal is for you to really get why neutrinos are just so unique.
Okay, let's do it. Starting with the big comparison. Neutrinos versus photons. Both fundamental, both zipping around, but underneath, very different characters.
Totally different. I mean, look at their basic nature. Neutrinos are leptons, so fundamental matter particles that don't feel the strong force. And they're fermions. They have this half-integer spin property.
Okay, leptons, fermions, and photons.
Photons are different. They're the quantum bits of the electromagnetic field light, essentially. They are bosons, and they have an integer spin, specifically spin 1.
So wait, just to simplify that, neutrinos are like building blocks of matter, and photons are more like messengers carrying forces.
That's a really good way to think about it. Yeah, fermions, like neutrinos, make up the stuff, and bosons, like photons, carry the messages, the forces between the stuff. They tell particles how to interact.
Right, and mass is another huge difference, isn't it? We didn't always know neutrinos had mass.
No. That was a major discovery. It turns out neutrinos do have mass. It's incredibly tiny, way less than an electron, but it's definitely not zero. That's still a hot research area, finding the exact mass.
But photons, still massless.
Still firmly massless. And that tiny neutrino mass, it makes a difference.
Speed, right? Having mass means you can't quite hit light speed.
Exactly. Neutrinos travel just under the speed of light. They get very, very close at high energies, but technically always a fraction slower because of that mass.
Whereas photons, being massless,
always travel at c in a vacuum, no question.
Okay, now something they do share is being electrically neutral.
Correct. Both neutrinos and photons have zero electric charge.
But that's kind of where the similarity ends, especially when you talk about how they interact with everything else.
Oh, absolutely. This is maybe the most crucial difference. Neutrinos mainly feel the weak nuclear force and gravity. They're almost completely indifferent to the strong force and, importantly, the electromagnetic force.
So they don't really see electrical charges?
Not directly, no. But photons, they are the electromagnetic force. That's their whole deal. They carry it, they interact constantly with anything that has an electric charge.
So, like you said before, neutrinos are the ghosts slipping through walls, while photons are, constantly bumping into charged things.
That's a great picture, yeah.
Yeah.
It really captures how differently they experience the universe. And then there's another layer of weirdness with neutrinos. The flavors.
Oh, the shape-shifting. This is wild. They come in 3 types.
3 types, or flavors.
Yeah.
Electron neutrino, muon neutrino, and tau neutrino. And the really mind-bending part is they can actually change from one flavor to another as they travel.
That's neutrino oscillation.
That's oscillation. And it's not just some quirky detail. It's fundamental proof that they must have mass. It has huge implications for physics.
Wow. And photons don't do anything like that?
Nope. A photon is a photon. We talk about different energies or wavelengths, radio waves, X-rays, gamma rays, but it's all the same fundamental particle, just with different amounts of energy, no flavor changing.
Okay, so quick recap on these two. Neutrinos are matter particles, fermions, tiny mass, neutral, interact weakly, and change flavors. Photons are force carriers, bosons, massless neutral, interact electromagnetically.
You get it. Big differences.
So how do neutrinos stack up against the other radiation types we hear about, like from nuclear stuff? Alpha, beta, gamma.
Right. Good transition. These often come from radioactive decay. Let's start with alpha particles.
Okay, these are the heavy ones, yeah.
Relatively speaking, yes. An alpha particle is basically a helium nucleus. 2 protons, 2 neutrons stuck together.
So definitely not fundamental like a neutrino. It's composite.
Exactly.
Yeah.
And because it has 2 protons, it's got a +2 electric charge. Plus, it's quite massive compared to electrons or neutrinos, about 4 atomic mass units.
And that charge and mass must mean it interacts way more strongly than a neutrino.
Oh, absolutely. Alpha particles interact intensely through the electromagnetic force.
Yeah.
Lots of charge, lots of mass. That means they slam into other atoms really easily.
So they don't travel far.
Not at all. Very short range. A sheet of paper, even just a few inches of air, stops them easily.
Yeah.
Total opposite of a neutrino.
Okay, makes sense. What about beta particles? There are two types of those.
Yep. Beta decay can produce either a high-energy electron, which we call beta minus, or its antiparticle, a positron, which is beta plus.
Electrons and positrons, so they have charge.
They do. Beta minus has lightness 1 charge, beta plus has plus 1, and they have the mass of an electron, which, again, is tiny compared to an alpha particle, but still way, way heavier than a neutrino.
So wait, electrons are leptons, just like neutrinos, right?
Correct. Both are leptons.
But they still behave totally differently because of the charge and the mass difference.
Precisely. Beta particles being charged interact electromagnetically, much more strongly than neutrinos do via the weak force. They penetrate further than alphas.
Right.
But you can still stop them with, say, a thin sheet of aluminum. A neutrino would barely notice the aluminum.
Okay. Alpha heavy and charged, short range. Beta lighter, charged, medium range. Neutrino. Almost nothing, neutral, goes through everything. What about gamma rays?
Gamma rays. Well, fundamentally, gamma rays are photons. Just really, really high-energy photons, typically produced in nuclear processes or other high-energy events.
Ah, okay. So the comparison between neutrinos and gamma rays is really the same as neutrinos versus photons, just scaled up in energy.
Essentially, yes.
Yeah.
It's still the fundamental difference. Neutrino's a lepton, interacts weakly. Gamma ray is a boson, a photon, interacts electromagnetically.
Even at high energy, the gamma ray is still massless and feels that electromagnetic force.
Exactly. Its high energy changes how it might interact, sometimes creating particle pairs, things like that. But its fundamental nature as a photon, governed by electromagnetism, remains the same. Still very different from a neutrino.
So if we boil it all down, the key things separating neutrinos are really fundamental nature, this weakly interacting fermion with a tiny bit of mass, compared to the massless electromagnetic boson, photon gamma, or these heavier, often charged composite particles like alphas, or charged leptons like betas.
And that weak interaction is the absolute defining characteristic. It dictates almost everything else about them.
Yeah, it's the key. It leads directly to that incredible penetrating power, doesn't it? The whole ghost particle thing.
Absolutely. That's not just a nickname, it's descriptive. Neutrinos can and do pass through light years of lead without interacting. They stream through the Earth, through us, constantly.
While gamma rays, even though they're penetrating,
They are, yeah, highly penetrating compared to alpha or beta. Useful for medical imaging and such, but dense materials like lead will stop them eventually. Far, far less penetrating than neutrinos.
and beta, stopped by aluminum, alpha, stopped by paper. It's a huge range.
A massive range, all stemming from those fundamental properties.
Mm-hmm.
Charge, mass, and especially the primary force they interact with.
It really makes you think, doesn't it? Billions of these things going through your fingernail every second.
It's mind-boggling. And, of course, this extreme reluctance to interact makes them incredibly difficult to actually detect.
Right, you can't just like put out a net.
No, definitely not. Detecting neutrinos requires enormous detectors, often built deep underground to shield them from all the other cosmic rays and radiation bombarding us.
Why underground? Just to filter out noise.
Exactly. You need maybe a mile of rock overhead to stop most other particles. Then you have this huge tank, maybe filled with ultra-pure water or another special material, and you wait.
You wait for one of those trillions of neutrinos to actually hit an atom just right.
Just right.
Yeah.
And when it does, very rarely it can produce a secondary charged particle or a tiny flash of light. And the detector is lined with incredibly sensitive light sensors, photomultiplier tubes, to catch that faint signal.
Wow, that sounds painstaking compared to detecting photons.
Oh, but much easier. We detect photons all the time. Our eyes do it. For science, depending on the energy, we use everything from antennas for radio waves, CCD chips, like in cameras for visible light, scintillators or semiconductors for X-rays and gamma rays.
And the basic idea is the photon dumps its energy into the detector material.
Pretty much, yeah. It interacts electromagnetically, transfers energy, usually kicks an electron, and we measure that effect.
And alpha and beta being charged.
They're easier, too, because they ionize matter as they pass through. They knock electrons off atoms. Detectors like Geiger counters, cloud chambers, silicon detectors, they all work by spotting that ionization trail.
So the detection method is like a mirror image of the interaction strength. Weak interaction needs massive, sensitive, shielded detectors. Stronger electromagnetic interaction is much easier to spot.
Perfectly put. The way we see them is a direct consequence of how they touch the world.
Which brings us to the big so what.
Hmm.
Why does distinguishing these particles matter so much for us, for understanding things?
Well, precisely because neutrinos are so different, so weakly interacting. They are unique cosmic messengers. They carry information from places that light, photons, simply can't escape from.
Like the inside of the sun.
Exactly. The core of the sun, where nuclear fusion happens, photons produced there bounce around for maybe 100,000 years before reaching the surface. Neutrinos, they fly straight out almost instantly.
So they give us a real-time view of the sun's core.
A direct window. Same for supernovae exploding stars. The neutrinos get out moments after the core collapses, hours before the light bursts through the star's outer layers. They tell us what's happening deep inside incredibly dense, violent events.
That's incredible. It's like having a secret informant in the universe.
It really is. And studying their properties, those tiny masses, the flavor oscillations, pushes the boundaries of our fundamental theories, like the standard model of particle physics. It hints at physics we don't fully understand yet.
So understanding these differences isn't just trivia. It's key to probing the universe's biggest secrets and its fundamental rules.
Absolutely critical.
Thinking about how neutrinos just slip through almost everything, it really makes you wonder what else might be out there. What other particles or forces might exist that interact even more weakly or in ways we just haven't conceived of yet? Like, what new kinds of senses, what new kinds of detectors might we need to even start looking for them?
That's a fantastic question to ponder. The neutrino, this ghost particle, is a constant reminder that the universe we perceive directly might just be the tip of the iceberg. There could be whole layers of reality that barely interact with our normal matter and energy at all.
A very deep thought indeed.
It keeps physicists searching.
Well, thanks for going on this deep dive with us, exploring just how different neutrinos are from their particle cousins. It's amazing how these tiny, elusive things tell us so much.
It really is a fascinating corner of physics.
We hope this gives you a fresh perspective on these ghostly particles and the fundamental fabric of the universe. Definitely something to keep thinking about.